So good morning, everyone. Welcome. I have a hard task, which is in half an hour, try to describe the Earth observation program of ESA and also the tools that we make available for education in Earth observation. So I'll try to do it as fast as possible. Maybe you can interrupt me every now and then to ask questions, or in the end. And anyway, I'm staying here for the whole of the 3 days, so you are welcome to ask me questions all the time. I don't know if all of you are familiar with ESA. It is the European Space Agency. It's an intergovernmental organization for the purpose of exclusively peaceful exploitation of space and the development of space activities in Europe. All member states participate to a number of activities which are called mandatory programs. On top of that, there are optional programs which include Earth observation, which anyway is not the only program we have, although this is the only one that I will go through in this presentation. But we also have telecommunication, launchers, navigation, and so on. In particular, one of the main activities of ESA is in space science, with the development and launch of missions for, interplanetary missions, and study of, for example, the solar terrestrial interaction. This is the SO satellite orbiting in a Lagrangian point. But there are also missions to comets and other planets. Earth observation, which is the directorate I belong to, has developed since the 70s the series of the Meteosat satellites that everybody knows because they provide you daily with information about meteorology, and which was then followed by the Meteosat second generation series and then by METOP. And also missions like ERS-1, ERS-2, and ENVISAT that you will see and study during these 3 days. And finally, the Earth Explorer series with the one Earth Explorer, which was launched a few weeks ago. And they include a number of observations of the Earth, the atmosphere, the ocean, and the gravity field now, which gives you an overall vision of the Earth, of the planet Earth, which was never attained in the past. So, as I said, the Meteosat series was started in the 70s. It's a series of geostationary satellites. You will see later what the geostationary orbit is. And they provide images of the Earth, whole hemisphere, every 30 minutes in the Meteosat case, and every 50 minutes in the Meteosat second generation case. And then this series were followed by a polar orbiter for meteorology, which is called METOP, which is the first in its kind. The ERS series, European Remote Sensing Satellites, consists of 2 satellites. The first one, which was launched in '91, which have the main payload, which is a radar instrument. It's called synthetic aperture radar. It's a very peculiar instrument which allows to take measurements of the Earth's surface in the microwave spectrum, and it is independent from weather conditions and from solar illumination. So you can have operational observations taken day and night, and whatever the meteorological conditions are. On top of that, with ERS-2 satellite launched 5 years later, an additional instrument was added for ozone monitoring. It is only in 2002 that ESA launched its huge, monstrous satellite, ENVISAT, which is the largest ever built satellite for Earth observation, with a series of 10 different instruments, not only in the radar, in the microwave spectrum, but also in the optical spectrum, and allowing to take a variety of different measurements of the Earth, giving a really overall complete observation of our planet and the interaction between the atmosphere, land, ice, and so on. And this satellite, which is now been orbiting for 7 years, allows to cover applications in the field of crop monitoring, biodiversity, deforestation, natural disaster monitoring, ozone, and so on. Here you have an overview of the different type of applications which are possible with this satellite, thanks to all its instruments. And you see radar images, so radar applications like, for example, oil spill monitoring in the ocean. Also, thanks to the radar instruments, you can perform differences in the phase measurements of two images and have a very precise information about ground deformation in the case of earthquakes, for example, or volcanic eruptions. This is another example of radar application of ENVISAT, which allow to measure the variation of the height of the Andaman Islands after the tsunami. And then on top of that, you have measurements for the atmosphere, pollution concentration, CO2, ice coverage of the Arctic and the Antarctic, and measurements of the effects of cyclones, which allow to combine radar measurements, which give information about the ocean surface, and meteorological or atmospheric measurements would give you at the same time information of the cloud, wind, and so forth. This is the cover of the brochure that you were given, and it should give you an overview, an idea of how these measurements are complementary, and they not only allow to cover the whole of the Earth's surface, but they provide you information which are really complementary in terms of biophysical parameters that you can measure, and go from displacement of the ground surface with a millimetric precision to variation of the coverage of the poles, because the radar instruments are very sensitive to ice, and state of the vegetation or pollution in the atmosphere. This is a sad recent application of radar measurements on board ENVISAT, and it gives you an information about the deformation field which was produced with the earthquake in Abruzzo a few weeks ago. And combining, for example, such measurements taken either in ascending or in descending geometry of the radar satellite, because with radar you can combine both instruments. Since you have day and night acquisitions, you can improve the geophysical model of the earthquake, which then allows you to better predict the hazard or seismic event in the area or in the neighboring faults. This is another application which is well known, because it was published on most newspapers, of the radar measurement of the oil spill produced by the Prestige tanker in the neighborhood of the Galicia coast. And this is again a unique measurement that you cannot have with the optical satellites. These are a list of the major scientific results of ENVISAT and also ERS. So they cover climate change, like global sea level rise, which is close to 3 millimeters per year. And they increase also sea surface temperature, and these are of course very important parameters for the assessment of the possible climate change or climate variations. You have a worldwide monitoring of the atmosphere and then of the pollution. This image here shows the NO2 concentration measured by Shamaki, an instrument on board ENVISAT, and you see the high concentration, for example, which was measured in this average time over China, which is now one of the main producers of NO2. And also oceanography measurements for the quantification of the chlorophyll concentration, tectonics, as we have seen before, thanks to the ground deformation measurement, and the monitoring of the polar areas. By the way, it's an animation of the ozone hole measurement thanks to MVSAT. This is a set image of the very low Arctic coverage, which was measured by the radar instrument aboard MVSAT in 2007, which is the lowest that was ever measured, with an opening or a passage which was not existing before. And this is a combined measurement thanks to ERS-1, ERS-2 topics and MVSAT of altimetric data, which show a continuous trend of around almost 3 millimeters per year in the interval from 92 to 2005. So all these measurements are extremely important when you see the report of the International Panel for Climate Change of 2007, which reports the conclusions of the scientists thanks to the overall available measurements, so satellite measurements and in situ measurements, and the integration into models for the forecast of the global change or climate change, which foresees up to between 2.4 and 6.4 degrees until the end of the century, so a temperature increase, global temperature increase, which doesn't mean that the increase would be homogeneous, but you would have extreme temperature variations which are different in different areas. And this would imply possibly an ice-free Arctic in the second half of the century, or an increase of extreme variations of precipitation, which means drier, arid regions and more wet, humid regions. Also, higher, stronger storms and in regions which are subject to this type of phenomena, a weakening of the Gulf Stream, and the sea level rise, which could reach almost half a meter in the end of the century. So given this catastrophic forecast of the models, it is very important to have precise and reliable measurements, including from space. And ESA has initiated a program for climate change, where the full archive of our data will be made available and exploited to contribute to observation of what are called the essential climate variables for the international community. These type of measurements are important not only for science and for modeling, but also for operational applications in near real time in the case of natural catastrophes. And we provide this data together with all the other space agencies which contribute to the agreement in the frame of an international charter for space and major disasters, which is supposed to provide in a very short time, in near real time, data and maps of damaged area to the civil protections of countries which are hit by natural disaster. And these data are now so important for the international community that we are starting a series of operational satellites for Earth observation, which are called the Sentinel. This is the space segment of the GMES, the Global Monitoring of Environment and Security, which is a European initiative, not only by ESA, but also by the European Commission, which by starting in 2012 will launch a series of satellites for the continuous provision of the measurements that we have seen so far. So this animation, which doesn't work, would show a simulation of the constellation of satellites which would be available for GMES, the space component, and that would provide a continuous observation of the whole Earth with a rapid access. On top of that, we just launched the first satellite of the Earth Explorer mission, which is a series of satellites for the scientific study of the planet Earth. And the first one, GOES, or GOCE, which was launched on the 17th of March successfully, thanks God, will provide a precise, never attained before, measurement of the gravity field and the city-state ocean circulation. What we are going to provide you in these 3 days are a series of tools that you can use to teach Earth observation as a mean to better explain geophysics, geography, science to your students in the class. And the first thing that, of course, students have to understand is what is Earth observation and why we developed this, this technique. And in fact, the answer is very easy, because the answer is that thanks to Earth observation, we should be able to respond to the old question, where we are and how our planet works. So satellites, of course, are not only artificial satellites. The natural satellites that we know since many centuries, and whose orbits were precisely determined and modeled by Galileo, Kepler, and Copernicus, of course, gave the idea in the 50s to develop artificial objects which follow this kind of trajectories and continuously observe the Earth, taking measurements for the Earth's surface. At the beginning, of course, it was not for science, it was more for military purposes, but as usual, this development gave a push to the scientific technique that we use nowadays for the study of our planet. There are 2 important types of orbits that you have to understand and to explain to pupils. There are the geostationary satellites, which are moving around an orbit of 36,000 kilometers from the Earth's surface on the equatorial plane with the same angular speed as the Earth, so allowing to have a constant observation of the same hemisphere. And this is the case of the most common meteorological satellites. And you have, and this is the type of images that you can get. And then you have polar satellites like ERS and MBSat that I showed earlier. And these are satellites which orbit on a plane which contains almost the poles of the Earth. That's why it's called polar satellites. And thanks to the Earth rotation, the combination of such orbit and the movement of the Earth allows to map the complete Earth surface. And this happens after more or less 35 days in the case of ERS and MBSat. So in the case of these polar orbits, which are also called low Earth orbit because they have a height of around 800 kilometers, is it possible to image the Earth with a precision like the one that I'm showing here, but also up to metric resolution in the case of commercial satellites, which are normally developed by private companies for non-scientific purposes, and that you are most knowledgeable to thanks to Google Earth. Those are the kind of image that you will find there. So the tools that we can provide you to help students understand these techniques, they are available mostly on the web, but also on the CDs and DVDs that we'll distribute you today. There is also, of course, ESA is not the only agency providing such measurements. There is an agreement between ESA and other space agencies to develop jointly such tools. And in particular, there is a mechanism which is called CEOS, the Committee for Earth Observation Satellites. And on its web page, the address is here, you will find the links to all the tools which are developed by the different space agencies. Our main tool for secondary school Earth observation teaching is called EduSpace. It's a web-based program on the web, which not only gives lectures about Earth observation and its applications, but also provides you with real satellite data that you can download from an image data bank, and a software and a GIS which are quite easy to use, and they are adapted for secondary school teachers and students for the processing of these satellite images and the most common and easiest applications. By the way, this tool is completely free, of course, and it is available in 8 different languages, including Greek, which is the latest translation that we are doing. So in French, Portuguese, Spanish, English, German, Italian, and so forth. This is an example of the type of processing of satellite data that you can do with this software. You can perform the most common types of classification and image visualization, contrast, enhancement, and so on. Then there are other tools like DVDs and CDs, for example, for the understanding of the International Charter for Space and Major Disasters that I mentioned before. We have a school kit that will also distribute, that was distributed to you yesterday, also for secondary level. It's a hard copy so far, but we'll also develop a web-based with 11 different worksheets or chapters about Earth observation, the Earth views from space, Africa from space, volcanoes, flood monitoring, and so forth. And this is the type of triptychs that you got in the module that you got yesterday. There is also a CD for the Earth Explorer missions, not only GOES, but also the other ones which are coming. And a window on the world, which is a DVD in 2 languages, English and French, which is similar to Google Earth, but with, of course, a higher educational content, because you can not only zoom and visualize the optical images, but also see other type of measurements like atmospheric measurements and so on different parts of the world. And finally, the last one is the ESA School Atlas that you probably have got already. If not, you'll get in these days. It's an atlas of the complete world, which was developed using ESA and also not ESA satellite images. And it contains, on top of the book, also DVDs with exercises. And the DVDs contain the images which are in the atlas with the different bands, so that you can process the images using the software which is distributed by ESA on the EduSpace website, and make exercises which are suggested to teachers in this teacher handbook that you hopefully have got also. And finally, there are tools for primary schools, which I will not describe here. I think that among you, we have 2 or 3 primary school teachers, so we also have a number of tools for primary schools. Finally, the last day of this workshop, on Wednesday, you will have a description of a project which was developed by a consortium funded by the European Commission, which is called CEOS, Science Education via Earth Observation. So the purpose is not to teach you what ESA or the space agencies have developed, but rather to use these tools as a means to improve the understanding of the planet Earth and the different disciplines, using Earth observation as an additional tool. And so this concludes my presentation. I just would like to remark that Earth observation for us is an important tool for the explanation of different disciplines at schools, and this should start as soon as possible with the small kids, which will become the policymakers of tomorrow. And it's very important to make them aware, since they are youngest age, of the importance of our planet and its preservation, and the impact of the human development so far, and the fact that we should more and more go for a sustainable development of our planet.
Said heliocentric, heliosynchronous?
Yeah.
Francesco, the person asking the question is Nicole Laduc, who's one of the teachers working with NSF for 1 year or 2 years. If you ask a question, please introduce yourself.
Oh, sorry.
Yeah.
So why is it called heliosynchronous?
Yeah. The type of polar orbiters that we developed are called sun-synchronous, and this means that the orbit that was selected is not an orbit which is really inertial in space, but in fact it rotates along the year with more or less 1 degree per day rotation, in order to follow the apparent rotation of the sun around the Earth. And this is due to the fact that we would like to have a constant sun illumination on our acquisitions. And also, so is it important for optical measurements, but also for the satellite power, in order to have a constant power to the satellites thanks to the solar panels.
So to go faster because it's closer?
No. It is a circular orbit with the 800 kilometers height from the Earth's surface. And what is happening is that during the year, thanks to the particular combination of the satellite elements, this orbit is rotating around the Earth rather than being stable, as it should normally would be the case. And this is done on purpose in order to follow the apparent sun rotation around the Earth during the year. But the speed is a constant speed around the Earth. And the rotation is also a constant rotation around 1 degree per day.